Frank Tip from Northeastern University. So testing in general is one of the most effective techniques in finding programming bugs. However, as the system evolves and it becomes bigger, effective manual testing becomes a challenge. So it's a common case that we often face a shortage of resources. It could be time, could be money, could be just a number of people that we need to test the system. In this situation, the automated test generation approaches come to rescue. They help reducing manual effort by generating test cases in a fully automated way. Moreover, these approaches have proven to be very effective in finding programming errors in even well-tested and mature system. So this definitely should make developer happy. Let's illustrate a few examples on how the automated test generation would work in practice. So you can see two functions. One function returns a Boolean value which indicates whether a string is contained in another string. Another function returns the size of the array. So test generation approaches generate effective tests for these functions. So one of the reasons can be that these functions require relatively simple inputs, such as strings or arrays. However, the automated test generation becomes more challenging for functions that take more complex input. For example, here we have a function that takes another function as an input. We call these functions higher-order functions. So during the execution, higher-order function at some point executes the input function. So for the rest of the talk, I will refer to input function as a callback function. And test generation for higher-order functions still remain a largely unsolved problem. And this problem becomes more complex when it comes to dynamic languages, such as JavaScript. So to generate effective tests for higher-order functions, we need to address several challenges. The first challenge actually concerns the position of the callbacks. So in dynamic languages, we don't have a notion of type signature. So essentially, callback function can be expected at any argument position. The second challenge is how do we generate callbacks that influence the execution of a program? In the third challenge, we are concerned about how do we chain multiple calls to higher functions in order to generate effective tests? And finally, if we use these tests to find programming errors, we are actually wondering, is there any type of behavioral differences of errors we can detect that are related to how the function under test executes the callback? So, and in this talk, I'm going to present LambdaTester. That is our solution for testing higher-order functions in dynamic languages. The input to our approach are functions we want to test, plus optionally some setup code. Setup code in general can be used by a developer to provide some values that could be used in generated tests. So the first step of the approach is inference of callback position. And the second step actually generates the test by using feedback-directed test generation approach for generating method sequences. Finally, the output are just generated tests. So let's take a closer look into each step. To infer callback position, LambdaTester generates a test that contains the method call, and it passes a callback at each argument, at each argument position while leaving other arguments unconstrained. For example, LambdaTester would first generate a call to function we want to test, and it would pass an empty or dummy callback as a first argument. Then the LambdaTester would start executing the function and observing whether the function calls the callback at some point. If the callbacks is executed, the Lambda tester would conclude that the function expects the callback as a first argument. Then it would continue by passing a callback as a second argument, and so on up to some number of arguments. Finally, the output of this step would be all argument position where the function we want to test expect callbacks as input. So the second approach consists of generation of method sequences. And this step is inspired by existing feedback-directed test generation approaches. So probably the most famous one is Rundup, and we use a similar idea to drive the execution of to drive the generation of our tests. So in general, the Lambda tester would generate the method call, would add this method call to the sequence, execute the sequence, and collect the callback on this execution in order to drive generation of next method call. So the feedback in our case is whether the test crashes or not, and what is the return value of the last method call. So this return value is used to a pool of values that serve as a potential input for the next method call. If the test crashes, or we reach the maximum size of method sequence, the Lambda tester actually stops test execution and it outputs the test. So finally, the test consists of a setup code provided by the developer, which is optional, and the sequence of generated method calls. So as I already mentioned, feedback-directed test generation is not something new. But in this work, we contribute to the feedback-directed test generation approaches by combining them with the different callback generation approaches. LambdaTester supports 4 different types of callback generation approaches, namely cbempty, cbquick, cbmine, and cbwrites. So let's take a closer look into each of them. cbempty is the simplest possible callback generation. So it's just empty function. It doesn't do anything, doesn't have any computation, either return value. And some of the existing test generation approaches use these sort of inputs whenever a callback is expected. The second approach, cbquick, uses callbacks generated by quick check. So for those of you not familiar with the quick check, it was test generation approach originally designed for Haskell programs, but they have implementation for JavaScript. And the key property of callbacks generated by quick check is that they return random values, but they do not perform any additional computation. OK, then we thought, can we be more effective if we, instead of using techniques, existing techniques for callback generation, we just mine callbacks that are used in existing code? So the idea here is to parse function expressions that are passed to methods that have the same name as the function we want to test. And during test generation, Lambda tester just randomly selects some callback from existing code by parsing function expressions. Finally, I'm going to present in what we believe is the most sophisticated approach and most effective approach for callback generation called cbwrites. And cbwrites is an approach based on dynamic analysis of memory reads after the callback executes. So let me give you one example. Here we have a function that we want to test. At some point, this function will invoke the callback. And from this point now on, we are interested in all memory reads that are read by the function under test. So in this case, these are return object of the callback. And this is also the property A of the X argument object. It's also important that we consider only reads to memory locations that are reachable from either arguments or base object, or global state, because we can generate a callback function that manipulates these values. So once we have these memory locations, we randomly sample some of them and synthesize the callback code by assigning random values to these memory locations. So by generating callbacks in this way, we make sure that the generated callback influences the execution of a function under test by modifying the memory locations that are read from the function. So far, I presented you our solution for testing higher-order functions in dynamic languages. And we implement this approach as a tool for testing functions written in JavaScript. And we assess its effectiveness by finding bugs in polyfills. So for those of you who are new to JavaScript world, polyfill is implementation of some API that was not supported by older browsers. And since the browsers always evolve and they start adding new functionalities, it's also important from the developer point of view to have this cross-browser compatibility. And that's where the polyfills actually come into place. So we find bugs in polyfills by using differential testing. So we execute our tests with the polyfill implementation and with the native implementation. And we say that the polyfill is buggy if the native implementation gives a different output than the polyfill implementation. So we use a couple of oracles to find behavioral differences between polyfill and native implementation. Some of them are very standard oracles that are used by other test generation approaches. But we also consider two novel oracles related to how the callback is called, namely state of the callback arguments and the number of callback invocations. So in our evaluation, we test two sets of polyfills. Let's call it like this. So the one set of polyfill is called on array objects like map, reduce, or filter, because all of these methods are higher-order functions. And another set of polyfills are defined on promise libraries. So you're definitely going to hear more and to learn more about promises in next talk. But shortly, the promises are objects that capture the result of some asynchronous execution. And we compare 4 feedback-directed instances of LambdaTester with the base approach. It is completely random test generator that is also unaware of any callback and never passes a callback as argument. So we assess the effectiveness of LambdaTester by generating 1,000 tests for each approach and polyfill combination. For example, for a reduce function, we generate 1,000 tests for the base approach, 1,000 tests for CBMT approach, and so on. There are 3 research questions we want to answer. The first one is, what is the effectiveness of our tool when it comes to finding behavioral differences? What is the effectiveness when it comes to coverage? And what is the efficiency of our approach? So the first question is, in how many libraries LambdaTester finds behavioral differences? And this graph illustrates the result. On the x-axis, we see the approaches we consider. And on the y-axis, we see the number of libraries in which each approach finds at least one behavioral difference. So based on these results, we conclude that CB writes approach is the most effective approach. It finds behavioral differences in 12 out of 13 libraries. CB mind approach is also very effective. It finds differences in 11 of 13 libraries. But the base approach doesn't find any behavioral difference. So now we show what types of behavioral differences each of these approaches find and how many of them. So on the x-axis on the graph, you can see the types of behavioral differences. I hope they are kind of understandable. So, and on the y-axis, there is a total number of behavioral differences found by each approach. So from this graph, we can also see that CB Wright's approach outperforms other approaches when it comes to all types of behavioral differences. And what is also interesting that it finds some kind of differences that were not detected by the previous approaches. For example, CB Wright's approach finds non-termination errors, while other approaches don't find such errors. And in this example, I'm going to give you an instance of a test that finds this non-termination error. We believe that this example is very interesting because the bug we detected is very serious. The key point here is the last method call. And in this last method call, the callback we generate returns a variable that should be used to assign the result of the method call. So what it does, it creates a circular promise dependency, and the native implementation just aborts this execution. It throws a type error. It says, OK, the chaining cycle is detected. I'm crashing the test. However, if you run this test with a Q library, the Q library just runs and runs and runs and never executes. So doesn't output anything, and it causes non-termination. Second interesting example of the bugs we found is in Polyfill IO library. So in this case, LambdaTester passes a callback that changes the length of the base object. And this write was suggested by our dynamic analysis. So the native implementation returns an array of 3 elements, while the Polyfill IO implementation returns an array of only 1 element. So when it comes to coverage, we measure statement coverage. And this graph shows the average statement coverage achieved by each approach over all benchmarks. So also when it comes to coverage, we conclude that CB Wrights is the most effective one, and it achieves, on average, 75% of the statement coverage. I would like to conclude this talk. In this talk, I presented LambdaTester, which is a test generation framework for high-order functions in dynamic languages. It's automatic and feedback-directed. It generates tests with non-trivial callbacks. We evaluate the effectiveness on LambdaTester on several instances of the framework based on the callback type, and we show that LambdaTester is effective in finding unknown differences and also increasing the code coverage. So the framework is available on the link you can see on the site. On the slide, it's also artifact evaluated and also available at ACM Digital Library. So thank you for your attention, and I'm happy to answer your questions.
Thank you very much. First question.
So this is a rather silly question, perhaps, but I'm just curious. So does the coverage of CB Write sort of subsume the coverage of CB Mind and such? Or would you say you would really want to use multiple techniques and the combined coverage is going to do better?
No, we just wanted to combine multiple techniques, so it's not necessarily that it substitutes the coverage of CB Mind.
Hi, thanks for the talk. So one of frequently when you have callbacks to higher order functions, there's a contract on the callback, right? So you say the callback must do X or must do Y in order for the call to be valid. Does your framework take into account any sort of contracts on the callback functions?
No.
Okay.
And for the polyfills we tested, we are not aware of any such contract.
Okay. Thank you.
Hi. Great talk. I have a slightly related question. For the CB Write strategy, as far as I know, it's not that easy in JavaScript to declare that an object property shouldn't be mutated. But I'll bet a lot of libraries aren't expecting that when you pass in a callback, it's going to arbitrarily mutate the fields of the parameters that you pass in. So I was wondering if you guys had any thoughts on how to deal with this. Maybe it doesn't come up with the differential testing of polyfills, which should be very robust to almost anything that you pass in. But for a typical user library, do you have any thoughts on how to not have these callbacks just wreaking havoc on the objects that you pass in?
Yes, I mean, I agree that some of the generated tests could be silly in that sense, so may not be representative of what the developer would write as a typical test. And one of the feedback we got, for example, for this bug was, okay, it's great that you found it, but like this is not something that happens often. We still think that testing, functions with strange inputs is effective technique to find bugs in this case in promise libraries or array polyfills.